Hi everyone, my name is Saborno Isaac Berry from Berry Science Lab, and today we're going to talk about the most popular form of encryption, or at least the simplified version of it, RSA encryption. This is actually an acronym of the names of its three inventors. Let's see if switching markers does any good. Okay, yeah, that's better. Okay, so first of all, how do you encrypt something? How does it work? Well, let's say Alice wants to send a message to Bob, but Charlie has his own nefarious reasons for looking into the message exchange. Let's say Charlie is a malicious hacker. Alice is sending, I don't know, some credit card info or something to Bob, and Charlie is in desperate need of money. So he wants to get all of that credit card data. So, how can we make sure Charlie cannot have any access to this line of info? Well, here's what happens. Alice is going to use a public key, right? So, this key is actually not a key. She's going to put a lock, more like, on her message. So, she's not actually going to send her real message. Instead, what she's going to do is she's going to encrypt it using a publicly available lock that everybody knows how to use. So she's encrypted it, and now it looks like this. So then, instead of sending this, she just keeps that on her own end and sends the locked info to Bob. And this bypasses Charlie. How? Well, Bob has a private key on his end that he's able to use to unlock it. Now, everybody knows what the lock is, but nobody knows what the key is except Bob. So, Bob is the only one that's able to transmit the publicly available information, this string, back into what Alice intended for him to see. Okay, so how can Charlie not figure out how to decrypt it himself? Well, what we want to do is make sure the lock is easy to put on and hard to take off. It's very easy to put on and it's very easy to unlock if you already have the key. But if you don't have the key, you can't use a credit. Oh, wait. You can't use a postcard to unlock it. You can't use a lockpick. It's much harder to unlock it when you don't have the key than, well, it's much harder to get the information if you only have access to the locking method. It's like trying to break into somebody's house, except for some reason you don't have a lockpick and you also don't have a postcard. It's going to be pretty hard for you to figure out what the perfect key to unlock this door is going to look like. So, what we need to do is have some encryption method that is easily applicable. So, we want Bob to be able to see this message pretty much instantly. I don't know, we want this decryption process to take 1 second. Because if we overcomplicate the encryption process just to make sure the decryption process is also complicated, then it's going to be inconvenient for the user on the other end too. So we want to make sure there's some sort of mechanical advantage. It takes a very short amount of time with the key, but it takes a very long amount of time without the key. That's what we want to do. We want to make sure that it's very easy to use, very hard to find. So how do we do that? Well, what's one thing that you find easy to do that's hard to reverse in mathematics specifically? I mean, if you like vandalize a building, it's pretty hard to undo that, but that's not mathematical. So, prime multiplication is a very hard thing to reverse. Multiplication in general is hard to reverse. But adding the prime really seals the deal. So, let me do something in my head real quick. What is it? Okay, let's see if you can figure out the prime factors that make up this semi-prime, 989. I'm going to give you 1 minute. Just pause the video or something, I don't know. As you can see, even with a very short number like this, it's really hard to figure out how to actually get the factors. And what you would actually have to do in order to find the divisors is, there's a very nice proof you can show, that if you have some number n that is composite, there must exist a prime factor p, a prime divisor of n, that's less than its square root. Otherwise, we could break n down into at least 2 prime factors, probably more, and if all of those were greater than or equal to the square root of n, well, first of all, if both of them were equal to the square root of n, then they wouldn't be distinct factors. Okay, I guess I can put that. So, if all of the prime factors were greater than the square root of n, then you'd have something greater than the square root of n multiplied by the square root of n multiple times, which by definition has to be greater than n. But that's the key part about it being composite, which means it has to be composed of the product of 2 or more distinct primes. Well, no, 2 or more primes, not distinct. Okay, so now the square root of 989, well, I'm aware that the square root of 1024 is 32, so the square root of 989, well, 31 squared is, I think, like 901 or something. So it's a little bit above 31. So now what we would have to do is check every single prime below 31. 31, 29, 23, 19, 17, 13, 11, 7, 5, 3, and 2. We would have to check 11 primes via division. And now, let's see how long it takes to, well, find the factors of this. Well, we'll find one of the factors less than the square root. The other one necessarily has to be greater. So, we start with 31, right? How long does it take to divide 989 by 31? Well, step 1, you multiply 31 by 3. Multiplying 31 by 3 gives you 93. So that's one step so far. Now subtracting is a second step, and you get 59. So then you get, well, 31 times 2 is greater than 59. So you find that 31 is the biggest multiple of 31 that's less than 59. then you subtract that and you get 28. So subtraction is another step, and then you have to compare it the final time and see that it's less than 31. So 5 steps so far. Okay, so we had a non-zero remainder, scram. Let's try 29. Well, 29 times 3 is, I think, 87. So that's another step added to the count. That's 119. 29 times 4 is 116. So that's another step added to the count. Actually, this subtraction was another step. This was a third step. And subtracting it again to get 3 takes a fourth step. And then the comparison, the fifth step, shows that this is not divisible. Okay, what about 23? Well, 98, 23 times 4 is equal to 92, I think, yeah. So let's try that. And that gives us 69. And then 23 times 3 is exactly 69. So this subtraction was one step, and 23 times 4 in the first place was another step. And then getting 69, multiplying is one step, subtracting is another step, and you get 0. Finally, we figured out that 23 is one of the factors. And you can actually write down the quotient, which is 43, which means that it took a whopping 14 steps on a lucky day to figure out one of the factors of 989. Yes, I multiplied 43 and 23 in my head to get 989. I knew all of this beforehand. So let's see. Took 14 steps to find them, while you only knew the encrypted version. Now let's see how long it takes to actually create this encrypted version. 23 times 43 is equal to, well, we counted multiplications as one step the whole time. But I mean, this is 9. This is 12. Wait, can I do that? Yeah. This is 6. This is 8. And I guess if you're pedantic, you could say there were 4 multiplications. So, overall, it took 4 steps. No, but I still, okay. I guess, let's say there were 2 multiplications in that entire thing, because I counted things like 23 times 4, which is actually this, so it's technically 2 multiplications. So to be fair, I'm going to do something like this. So it looks like it took 7 times less work to calculate this key than to decrypt it, than to break it into its factors. And finally, I mean, how many steps does it take to divide? Only 4, as we saw before. So this is the breaking time, this is the creation time, and this is the decryption time. So this is how long Alice is going to take, this is how long Bob is going to take, and this is how long Charlie is going to take. As you can see, there's a huge imbalance on Charlie's side. And that imbalance only grows as I start adding more digits to this number. See, some messaging apps, like, I don't know, WhatsApp, for example, use numbers, prime numbers, that are around 300 digits long. Not 3 digits long, like we just saw, 300 digits long. And special applications for, let's say, government security take, I don't know, unspeakable amounts of digits, except in, specific cases. Okay. So, now we know prime multiplication is very easy to encrypt with and very hard to decrypt with. And so, that's exactly how RSA encryption works in a simplified manner. In reality, well, you can look it up on its Wikipedia page. RSA encryption is a little bit more complicated than that, but it essentially relies on the principle that if I multiply P1 and P2 and only show you the final result, you will have a very hard time figuring out P1 and P2. But if I give you P1 and P2 and I ask you to multiply them, or if I give you P2 and A and I ask you to divide one by the other, you're going to have a much easier time. So Alice gets this, Bob gets this, but Charlie gets this. And that's an issue for Charlie because it takes a hell of a long time to do anything with just this. So that's it.